Okay.
Good afternoon. My name is James Wooster, and I'm here with Alex Campbell and Andy Osler. We're here to tell you guys about our ECE 542 final project, which is the money machine. According to Warren Buffett, all you've got to do to be successful in the stock market is buy low and sell high, which, as we all know, if it was that easy, we would all be rich by now. So the goal of this project has been to create a tool that could help people do just that, know when to buy low and sell high. And so for the scope of our project, what we've done is we've analyzed Home Depot in particular stocks for two reasons. One is that they have a long history of stock data that we can go to and reference. And two was because they seem to be a relatively stable stock. They don't seem to fluctuate as much with outside influences as some stocks like Tesla. Next slide. So in order to make our predictions, the network will take in the following 5 features for each and every day. It's going to be the high, low, open, close, and the volume of all stocks traded for that particular stock. And what we'll do is we look at 40 days time frame of data for each one of those 5 data points that we feel like will give us a pretty good picture of how that stock has performed over those 40 days. And from that, we'll try and predict the exact closing price of each of those next 5 days. And then based on the final 5th day stock prediction, our algorithm will say to the user, hey, you should buy, sell, or hold this particular stock. So during our research, we concluded that a recurrent neural network would serve us best. This is because they can handle continuous time series data better than most networks. One of the problems or challenges with RNNs, though, is that the amount of memory in the network is limited. And so to combat this, we found that using LSTM nodes would give us that longer term memory that we need to predict values for 5 days.
All right, so we chose 1 year's worth of data for the Home Depot stock. We chose this time frame because a stock's price can fluctuate drastically in longer time spans, and we wanted to give our network the best chance it had at predicting future stock prices. We obtained our data from Yahoo Finance, which was really nice because they output the data in a CSV file, which we were able to import into our Python script using pandas. In our proposal, we noted that our network would not take in outside influences like news articles, and therefore it could not make any changes due to natural disasters or pandemics. So to avoid the COVID-19 pandemic that we're currently in, we chose a time frame from January of 2019 to January of 2020. It's also good to note, since we used a multivariate data as our input, we had to standardize this data before it was input. Next slide. So here we have a plot of our data, our 5 features that we were inputting into our network before it was standardized. As you can see, open, high, low, close, they're all pretty much the same shape as each other, which is good. It means our stock was not highly volatile and there's not many changes going on. It's a very stable stock and it should be easier to predict. The last plot at the bottom is the volume. Usually higher volume means that the stock is more volatile on that day. There's more fluctuation in the price. If you had a more volatile stock, you would see drastic changes and a lot more volume on those days that were more volatile. Next slide. So for our model, we chose to use an LSTM. Basically, since we were using an RNN, we were going to choose either an LSTM or a GRU. The reason we went with the LSTM is because it has more memory than a GRU, and usually it's more accurate on data sets with larger sequences. We chose to use Atom as our optimizer because it took the benefits of both stochastic gradient descent and RMS prop into account. We had to adjust our learning rate a little bit just to allow for our network to make different smaller changes in the weights before each epoch. Also, we chose a mean squared error loss. We chose this because it puts more emphasis on larger errors and forced our errors to be positive. Next slide.
So here you can see the results of our network. It's predicting the last 5 days after the 40-day window of our validation data. The blue dots are the actual stock prices for those days, and the predicted values are in red. So the loss is pretty low. It's pretty close to the actual value. The plot is actually standardized. It's based on the mean and the min and max, or the standard deviation of the prices within that range. So some of the issues that we had, we saw a lot of underfitting in our model. The training took a long time to happen, while our validation loss would drop pretty quickly. So we had a hard time combating this because we just have a small amount of data. So what we did was we used a couple different things. We tried regularization with L2 and L1 and L2 values, and that didn't really seem to work very well. But doing batch normalization seemed to help stabilize things more. Dropout helped increase our validation loss and allowed us to have a more stable loss curve for validation. We tried changing the network structure to a number of different nodes and layers, but we ended up having such a fairly small network with only a few layers and not very many nodes as well. So we tried both mean squared error and mean average error for our loss functions, but the mean squared error seemed to give us the best results. Another approach that we could have taken that we found for this type of a problem was using a CNN, which takes the window of the stock prices and puts them into a matrix similar to an image and can train on them in that way. So this is another way that we saw that we could have approached this problem as well.